We saw in the last video that rotational inertia, or moment of inertia as some people call it, takes on these different forms. So let's go through each one of these and do an example and see how we use these equations. First, let's look at this example. A simple pendulum. Simple means that all the mass is in the end, in this pendulum bob. All the mass is at the end, and the string is massless. The string has a length L, the mass is M, and it's swinging back and forth across this dashed line I drew. We want to know what's the rotational inertia of this object as it swings back and forth like that. So this is a point mass. All the mass is in a tiny dot in a point at the end of the string. So it's just the mass times the distance to the axis of rotation squared. In this case, the axis of rotation is where it's attached to the ceiling. And the axis of rotation is perpendicular to the page. And our mass is swinging in the plane of the page. So the distance from our mass to the axis of rotation, in this case, is the length of the string. And if we put some numbers in here, then we can solve for I. And we get 0.5 kilogram meters squared. Our units for rotational inertia are kilogram meters squared. Now let's look at a case where we have multiple point masses. Let's say we have 4 point masses connected by some kind of massless rods. So they rotate as a group. They rotate as a solid object. And let's make the axis of rotation through the origin. So our axis of rotation is at that point, and it runs perpendicular to the page, like this, and our object is rotating in the plane of the page. Or the axis of rotation is here, and the object is rotating about that axis of rotation. Let's make each of these rods a distance A. And let's start filling in what we know. M1 is located at the axis of rotation, so its distance to the axis of rotation is 0. M2 is located at distance A from the axis of rotation. So R2 is equal to A. M3 is located at distance the square root of 2 times A. And R4 is a distance A from the axis of rotation, as you see here. And let's let the masses just be whatever we numbered them. M2, 2 kilograms, M3, 3 kilograms, and M4, 4 kilograms. And let's let A be half a meter. Half a meter, quantity squared, is quarter of a square meter. And so we end up with 3 kilogram meters squared for the rotational inertia of these 4 point masses that rotate together as a rigid object about the origin. Now let's take a rod, and let's have the rod rotating about its end point. And what we do, we treat each little tiny chunk of mass like a point object. So we pick a little tiny piece over here at some arbitrary location, a little tiny chunk. We say that's a little infinitesimal chunk of the whole thing. We call that dm. That's how much mass is in that little tiny chunk. And we say, what's the rotational inertia of that little chunk? It's equal to its mass times the square of the distance to the axis of rotation. That would be this distance right here. That's the rotational inertia of one little tiny chunk of mass. Well, what do we do if we have multiple chunks of mass? We add them up. What are we adding over? The rigid object. We're adding up all the mass over this rigid object. So it turned into an integral. You may be asking yourself, what the heck is dm? How do I integrate that? Well, I'm going to show you. dm is the amount of mass in that little tiny chunk. So picture this for a minute. I take a long rope and I hand it to you. And I say, I want to know how much a little tiny bit in the middle weighs, but I don't want you to cut my rope. What are you going to do? You're going to weigh the whole rope. And you're going to come up with a density. You're going to weigh the whole rope and measure the length of the whole rope. So if this is L, I'm going to put an x-axis here. And we'll call this L, and we'll call this our origin, 0. We measure the whole mass, and we divide by the length. This is true. This is the density, the mass density of our rod, if it has uniform density. Now we know the density. If we want to know how much a little chunk in the middle weighs, well, we multiply the density times the length of that little chunk in the middle. So what's the length of my chunk over here? It's dr. If it's a distance r away from the axis of rotation, and the length is dr. I'm going to call it, if I put it along the x-axis here, I can call r x, and dr I can call dx. So dm, the mass of that little tiny chunk, is going to be my mass density multiplied by the length of that little tiny chunk. This is always true. dm is always equal to the density multiplied by the length. If the density is uniform, I can substitute the total mass over the total length for lambda. But this is always true, even if lambda is not a constant. So I go back to my function for I, and it's going to be the integral of r squared, and we just said r was x, dm. dm is going to be lambda dx. And what am I integrating over? I'm integrating over the rod. It starts at the origin and it ends at L. So I'm integrating x from 0 to L. And let's keep things simple right now. Let's make the mass density uniform or constant, which means it comes out of the integral. And I know how to do this integral. Lambda L cubed over 3 minus 0 And what is lambda? It's the total mass over the length L. So one of the L's cancels, and we have 1/3 mL squared. That's the rotational inertia of a rod rotating about its end point.